This is going to be a quick video on deriving the power rule. Oh, that's not the one I wanted. Deriving the power rule from the limit definition. So that's the one that I wanted. So let's take a look at f of x equals x to the fifth. And let's apply the limit definition to that function, which means we would have to multiply x plus h to do this, right? F of x plus h would mean x plus h times x plus h times x plus h to the fifth. Okay, I'm not sure if you covered this in Algebra 2, and if you did, you probably did it for about 5 minutes and don't even remember. Because there is, well, first of all, we have technology to do this for us now. For example, if I stop sharing here, all I did was I went to Google and I just typed in expand x plus h to the fifth. Okay. And I don't know why they switched the h and the 5. I'm really not sure why they did that, but here's the answer. I'm going to write it though backwards. I'm going to start with x to the fifth. But you should notice a nice pattern, like it goes x to the fifth, x to the fourth, and then this is actually technically h to the 0. So the powers of x go down by 1 as the powers of h go up by 1. Okay, and then we have some coefficients. The way that you actually get those coefficients, and it's not that you have to know this. I mean, this is just sort of an FYI. But if you've ever heard of what's over here, this is called Pascal's triangle. Okay, and Pascal's triangle is formed by adding the two numbers ahead of it. So always start with a 1 and end with a 1, then add these, add these, add these, and add these. So Pascal's triangle, it does some other things with combinatorics, but one of the things that it does is it gives you the coefficients that you need in a binomial expansion. So we know if we raise something, first of all, if we square something, when you square something, you get 3 terms. Okay, so there's always one more term in the answer than the power. So what you do is you find the row that has one more term in it than 5, okay, which would be this row. Okay, so that's how they got the coefficients. So then if I scroll down to here, so here's f of x plus h. It's all this big long thing. Okay, so the coefficients, there's a 1 here that we don't see, and then the 5, the 10, the 10, the 5, the 1, and the power of x starts at the greatest power, x to the fifth. H starts at the lowest power, h to the 0, which h to the 0 is just 1, right? Anything to the 0 is just 1. So really, this term is just x to the fifth, and this term is just h to the fifth, okay? But what we've been noticing in all of the problems we've done with the limit definition is you can always, whatever is here and whatever is here, add. We're doing 2 plus h, right? The answer you would get over here and the answer for f of 2, they would always, oops, I didn't mean to scribble across my page. They would always zero out, okay? So these are gone every single time. So then the mathematician said, well, if we know they're gone, then let's not write them. Then what happens is when I divide everything by h, well, anything that's going to maintain an h after division by h to the first is going to go to 0. So the only term where the h divides out is this one. Okay, so then mathematicians said, hey, we know these are all going to go to 0, so why write them? So what is easily The only term in that expansion that survives the canceling and the division by h is the second term here, which happens to be always the power in front, right? And then decrease the power by 1, because when we're moving through a binomial expansion, we always start with x to the highest power, and then this is x to the next highest power, right? So the power is always 1 lower, and it happens to be that the coefficient want to take the derivative of x to some and then decrease the power by 1. And that's what I get to do now instead of using limit definition. Okay, so the next video will be examples of putting this to use.